the information theory last quarter?
Oh, yeah.
Yeah.
You did?
Yes.
Morning. So have your homework graded here. You can come up after class. So next week, there's no homework for next week since we have the midterm. But please make sure you practice a lot of the problems that I may not have assigned, but for which I've given you solutions in the homework. So if you look at the homework solution for each of the homeworks, the solutions contain not only solutions to the problems that I assigned, but also solutions to a bunch of problems I didn't assign. And the reason I'm giving you those is because I want you to practice and then check your answers. Okay? And there will also be some practice questions, some of which we'll go through today, and the rest you should, I'll post the solutions for them, but you should try those as well for studying for your midterm. Okay. So let's see. All right, so what I'm going to do today is mainly a review and then go over some old exam problems, and if you have any questions, this would be a good time to go over those as well. Okay. So as I mentioned, you're going to be allowed one sheet of notes, one standard 8.5 by 11 sheet of notes. You can write anything you want on both sides of it. But aside from that, no books, no calculators. That's it. Okay, so in the review, I'm not going to go over every concept that we covered. I'm just going to go over some of the most important ones. It doesn't mean that if I don't mention something here that it's not going to be on the midterm. I'm just trying to hit the highlights of what we had. Okay, so we started with a review of probability density functions, and we went through a whole litany of different probability density functions, all of which are fair game, but the one that is the most important is, of course, the Gaussian, and you should certainly always remember what the probability density for the Gaussian looks like and what the formula for it is. X minus m squared. So this is for the scalar, so one-dimensional PDF. Now if you have a vector, the mean is also going to be a vector, and then you're going to have a covariance matrix, and then in that case the PDF is 1 over 2 pi to the n over 2 square root of the determinant of c minus the exponential minus 1/2 x minus m transpose c inverse x minus m. Okay? We talked about independence versus uncorrelatedness. And what we discussed was that the implication was valid in this direction. Independent implied uncorrelated, but in general, uncorrelated does not imply independence. One way to think about this is that if you have two random variables, x and y, if they are independent, what that means is that the joint density between x and y is px times py, which is a very strong statement. Whereas if the two are simply uncorrelated, that means only the expected value of x times y can be written as expected value of x, expected value of y. So if you forget which one is the stronger condition, you can always remember this, and you can clearly look at this and see that this is a much stronger condition than that one. Okay? Because this condition implies something about all the moments of the probability density functions, whereas this one is only talking about the first order moment. Okay? So with all of this in place, we also noted that the Gaussian was the exception. And what that means is that if two random variables are jointly Gaussian and they are uncorrelated, that's exactly the same as them being independent. And we showed that by writing this expression down with a diagonal covariance matrix, and we showed that because of that diagonal covariance matrix, that could be broken down into a product of a bunch of one-dimensional Gaussians, which basically proved the left-hand side. Okay, so you started with the right-hand side with the diagonal covariance, and you ended up with this, and that showed that the reverse implication was also true for the Gaussian case. Okay. Transformations of random variables, if you have a random variable x, which has, let's say, a covariance of x is, let's say, c, okay? Then if you do a linear transformation of this random variable, then covariance of y is A, C, A transpose. I'm writing this down not because I think it's a terribly difficult thing, but you shouldn't have to derive this every time, so you should just remember that if you have a linear transformation and A and B are two constants, right, constant matrices, a matrix and a vector, then this is just the answer. You shouldn't have to go through the derivation every time. Okay, so then linear algebra, probably the most important concepts are the singular value decomposition and the eigendecomposition. The eigendecomposition in particular for a general matrix, for any matrix that is diagonalizable, we can write C equals V D V inverse. Okay, where D is a diagonal matrix and V is not necessarily an orthogonal matrix. Okay, so this is just the general eigendecomposition. However, if C is symmetric, then what you have is you can write C equals V D V transpose, because V transpose and V inverse are the same, because V is now going to be an orthogonal matrix. So V transpose V is equal to identity, which means it's an orthogonal decomposition. Okay? Now, in general, what we have for the case of the covariance matrices like C here is that C is not only symmetric, but it's also positive definite. So those are the two conditions that you always want to keep in mind for covariance matrices. So covariance matrix is symmetric, positive definite. And what that means is you can write its eigendecomposition like this, C equals V, D, V transpose, where D is a diagonal matrix, D1 through Dn, Dn like this, where all of these numbers are going to be real and non-negative. Okay? And V is, of course, an orthogonal matrix. Okay, the singular value decomposition is you start with a matrix arbitrary shape. Let's say A might be like this, or it might even be kind of short and fat. This is US V transpose, and what's special about this is that U and V are both orthogonal matrices. Not orthogonal to each other, but U transpose U is U transpose equals identity, and V transpose V is V transpose equals identity. And the matrix S will have the same shape as A. So if A is like this, S will have the same dimension, and S will have a part which is a diagonal matrix, S1 through, let's say, SP. These are all 0 and 0 here. Okay? And P, if all of these numbers are written in this way, S1, S2, SP, if this last one, if the smallest one, is in fact bigger than 0, then P is in fact the rank of the matrix. Okay. What's important to remember here is that for the singular value decomposition, all of these S's, regardless of what A is, all of these S's are always real. Okay? And they're always positive. That's kind of the difference between the eigen decomposition and the singular value decomposition. Okay? Now, what if you start with a matrix A with the singular value decomposition, and you want to see how this is related to the eigen decomposition? Well, since A is not square, it strictly speaking does not have an eigen decomposition. However, you can do things like A transpose A. Okay? So if you do A transpose A, this is V S transpose U transpose U S V transpose. This is identity, so this becomes V S transpose S V transpose. Right? Now, if you look at this, this looks very much like the eigen decomposition that we had before, except that in the middle here you have S transpose S. S transpose S, this matrix here, is simply a square matrix of this size with the square of the singular values along the diagonals. Okay? And immediately you can see that these numbers are also positive, which means A transpose A is a positive definite matrix, and because V is orthogonal, it's a symmetric positive definite matrix, which makes sense because the way it's defined, right? You can think of this as the square root, or you can think of A as the matrix square root of A transpose A. Okay? And furthermore, you can see that the eigenvalues of A transpose A are nothing but the square of the singular values of A. Okay? All right, so that's how the two are related to each other. All right, so now a quick summary of the detection theory material. So the general framework for this is that you are given a bunch of data, which we typically stack into a vector, let's say x1, x2, xn. So this is a column vector. And we have two hypotheses. We have H0, which we call the null hypothesis. under this scenario, you have a probability density function for all of these jointly under the H0 hypothesis and under H1, which we call usually the alternate hypothesis. This is the PDF X given H1. And now what we wanted was to somehow come up with an optimality criterion that would allow us to distinguish between which hypotheses the data came from. And one of the criteria that we used was the Neiman-Pearson likelihood ratio test. Okay? And what this involved was to compute the ratio of the probability density functions, PDF of x given H1, PDF of x given H0, and to compare this to a threshold gamma. And this result was optimal in that for a fixed probability of false alarm, this maximizes the probability of detection. And then you might wonder, where does this gamma come from? Well, once you fix the probability of false alarm, that automatically fixes the value of gamma, and the way it does so is through the following equations. So probability of false alarm is the integral over the region where this likelihood ratio is exceeds gamma, PDF of x given H0 dx, and PD is the integral of x bigger than gamma, PDF of x given H1 dx. Okay, and this is what we call the critical region. L of x exceeds the threshold. So the idea is you fix the false alarm, you know what this function looks like, you solve for the gamma, then that gamma determines what your probability of detection is, and you are guaranteed that that probability of detection is as large as possible for that fixed probability of false alarm. We generally measured the performance of detectors by plotting the false alarm against the probability of detection over this box, which goes from 0 to 1. This line here is what we call the chance line, which you get by tossing a coin and making a decision, completely ignoring the data. In general, the receiver operating characteristic curve, the ROC curve that you get will look something like this, which is better than tossing a coin. An important note here is that this is not the only way to measure the probability of false alarm and the probability of detection. In other words, if you started with this and you simplified it all the way down to a simpler test statistic, which we call T of x. Okay, so if you started with this and you somehow went through a bunch of steps and you came up with a test statistic that was T of x compared to, let's say, some gamma prime, okay, and this was H0 and H1. These numbers, or these quantities, can be calculated by integrating the PDF of T over the proper range. Okay, so this region of space can also be written in terms of T. The critical region can also be written in terms of T. Therefore, the integral can be calculated. In fact, it generally is much easier to calculate the integrals for the PD and the PF here as it might be to do it here. Okay, so that's really dependent on what problem you're looking at. Okay, so this was the basic framework, and if you remember, this framework basically allows you to fix your false alarm to whatever number you want it to be, which means that gamma basically ranges over an infinite range of values, which gives you this entire curve. Okay, it gives you a lot of flexibility. On the other hand, if you have some information aside from your data, which you want to incorporate into your decision making, such as how likely is this hypothesis versus this one ahead of time without having any data, you can do that, and what that will do is it will fix you at some point along this curve at an operating point, just like an electronic device that has an operating point. Okay? So this kind of describes the performance of the whole device, whereas once you have the prior information, that fixes you at some operating point. And the way we went about doing that was to minimize the Bayes risk, and the minimization of the Bayes risk criterion gave us a formulation that was very similar, but with a fixed threshold. It's probability of H0, probability of H1 times C10 minus C00 divided by C01 minus C11. Okay, so these were the prior probabilities of each of the hypotheses being true, and these were corresponding costs associated with making the wrong decision. Okay, so 1, 0 was the cost of choosing 1, when 0 is true, and so on. Okay, so this is the general minimum Bayes risk formulation. So this here fixes your gamma at some particular number. Now, special cases of this included the case when if C10 was equal to C01 equal to 1, and let's say C00 is C11 equal to 0. Okay? So then this term just goes away, and you have PDF of x given H1, PDF of x given H0, probability of H0 divided by probability of H1. And this, if you recall, was the minimum probability of error decision rule, or detection rule, where the probability of error we defined as probability of H0 times the probability of false alarm plus the probability of H1 times the probability of detection, 1 minus the probability of detection, and this is what we call the probability of miss. So misdetection. Okay, so this expression here, or this rule, minimizes this probability. Okay, so the point of going through all of this stuff is that there's a bunch of names that we've thrown around. Okay, and there's a couple more that I'll summarize. And the names can become confusing and a little overwhelming, but it's easy to remember them if you remember one as a kind of special case of another one. Okay, so the most general formulation being the likelihood ratio test, and these other ones all just fix the threshold. The most general way to fix the threshold is that one. And then a special case of that one is the minimum probability of error. And so the next one is what we call the maximum a posteriori. That's just a different way of writing this guy. Okay? So if we cross multiply these terms, then what you have is using the Bayes rule. You can write probability of H1, given x, probability of H0 given x is H1, H0. This is exactly equivalent to this. It's just a different way of writing it by cross-multiplying these guys and these guys, and simplifying or changing the expectations. And this is what we call the maximum a posteriori rule. Okay? And furthermore, another special case of this guy is if the two probabilities ahead of time are equal, so if the probability of H0, probability of H1 is equal to 1, what you get, PDF of x given H1, PDF of x given H0, let's just compare it to 1. H1 is 0, as opposed to gamma. And this is what we call maximum likelihood rule. Okay? There is a fundamental difference. I want to make sure there's no confusion about this. There's a fundamental difference between this and this. Yeah?
Probability of H0 equal to probability of H1 equal to 1.
1/2. Okay? So I just want to make sure that there's no confusion about this. Obviously, this rule here, which is the Neiman-Pearson likelihood ratio test, looks exactly like that, except that gamma is equal to 1. Okay? So this is a more specific case of that. But I want you to be clear about what the interpretation of this one is. Here, we're saying that the probability of H0 and probability of H1 are known to be the same. Okay? We know that they are equal. On the other hand, here, we're saying we don't know anything about them. Okay? One might be tempted to think, if I don't know anything about them, why don't I set them to be equal? That's not the same thing as not knowing anything about them. Okay? When you don't know anything about them, it means now you are free to choose this threshold because you don't have any prior bias. Okay? But if you somehow now restrict yourself, oh, because I don't know anything about them, why don't I just assume that they're equally likely? Now you're down to that one. You can't set this threshold arbitrarily now if you do that. Okay? Okay, so we moved on to matched filters.
Question.
Yeah.
In the previous day,
Yep.
if we set gamma equal to 1, then what will we obtain for PF, P of F?
Well, it will just be some number. I mean, it will be whatever probability a false alarm ends up being the answer. I mean, the equation is no different. You still compute the PF this way, except that now this will be fixed to 1. So the implication is that if you fix that threshold to 1, now both the false alarm and the detection are fixed. There's really nothing else you can do. Do you see what I mean?
And it doesn't have any interpretations?
If you set this to be equal to, if you set the threshold to be equal to 1?
Yeah.
Well, it does have an interpretation in the sense that if you remember, we talked about how the threshold basically is the curvature, is the slope of the rock curve, right? So what ends up happening is that if you set gamma to be equal to 1, you end up at a place where the tangent is parallel to this chance line. I don't know if that's a useful interpretation, but that's an interpretation.
But this doesn't have anything with the maximum likelihood ratio. That's
With the maximum likelihood,
maximum likelihood rule that introduced.
well, no, this is the maximum likelihood rule, right? I mean, if you set the threshold to 1, that is the maximum likelihood rule. That's exactly right. So I'm not sure. Did I answer your question?
I'm asking if you set gamma equal to 1 in the previous rule, does
Yeah,
it
if
have
you
any
set-
relations with this case?
Sure. If you set gamma equal to 1, you basically have the maximum likelihood rule. That's another way to think about it. Okay. Now, there's one thing to be a little bit careful about is if you look at this expression, because I can set these numbers differently, there's a bunch of different ways that I can get 1, right? Some of which will not be these two are equal, right? So the maximum likelihood rule comes from this very specific assumption, okay? So it's a little bit subtle. Maybe that answers your question, right? Okay. Okay, so the matched filters were the general Gaussian formulation where we had, let's say, two hypotheses, H0 and H1, where here X is just some noise, where W is a Gaussian with 0 mean and covariance C, and in this case it's S plus W, and in this case then the data is going to be mean S and covariance C. Okay? And for this, when we computed the likelihood ratio test, after simplifying everything to the simplest test statistic that we could find, we saw that T of X was X transpose C inverse S compared to some threshold gamma prime. Okay? And it's important to remember that this C inverse, if we break it into B transpose B, basically because it's positive definite, we can break it into two sort of square roots. Then this is just like the standard matched filter without the covariance matrix, or the covariance matrix being identity, because you can write this as X transpose BS, and then if you define Bx as a new random variable and Bs as a new signal vector, then it's exactly the same. So this is the general formulation that you want to remember. And most importantly, the performance of this type of matched filter is dependent on a quantity which we call d squared C inverse S. This d squared is sometimes called the deflection. Okay? You'll see if you look in the literature, you see the deflection criterion. This is the deflection criterion. So the performance depends on this guy. Okay? And we had, we also pointed out that there are two scenarios under which you can come up with this test statistic in which you have optimality. One of them is, in fact, if you have the Gaussian noise. Okay? But we also said that even if you don't have the Gaussian noise, if you define your optimality criterion to be the output signal to noise ratio, regardless of what distributions you have here, if you maximize the output signal to noise ratio, you still get an expression that looks like this. Okay. What's nice about this is that it's a linear detector. In other words, it's a linear function of the data. If we just think of C inverse S as just another vector, all you're doing is you're computing the inner product of X transpose with a vector. Okay, so computationally it's very, very easy to do. Okay. We also discussed how with this, because the performance of this type of thing depends on S transpose C inverse S exclusively, you have two components here. You have the signal component and then the noise component here. The noise appears in C inverse as a covariance matrix. So if you wanted to maximize your performance, you could choose how you select the S in such a way as to maximize the performance, and that gave us various guidelines for how one might choose to design a signal to maximize this criterion. Okay? And so, for instance, S would be related to the eigenvector corresponding to the smallest eigenvalue of C inverse and so on. Okay, so with the, from this, we got signal design criteria to figure out what our S could be. Okay. Okay, now let me move on to what we talked about more recently, which is estimation. So again, you're given some data which we collect into a vector, x1 to xn. And this also has a joint probability density function, p of x given theta. This is the unknown parameter. Okay, now let me just step back for a second to the detection scenario. Look at what we're writing here is p of x given theta, where theta is the unknown, right? What did we do for detection? We have p of x given hi, where I is the unknown, right? So the detection was just a simple case where you had two values, 0 or 1, h0 or h1, and you're trying to decide between. And the estimation scenario is in some sense more general, okay? So some of the intuitions that you have for the detection case do carry over to these problems as well. All right, so what is an estimator? An estimator, theta hat, is some function of the data, g of x. The two important characteristics of an estimator are bias, called b of theta, which is the expected value of theta hat minus theta, and the variance. And the variance theta hat, expected value, theta hat minus p theta hat squared. Okay, this is for the scalar case where I'm writing everything. Yeah.
Why don't you write the bias as a function of theta hat?
Because the theta hat is really, you see this expected value in here, right? Oftentimes what we have is the bias is either, what we're interested in is the bias as a function of the data and the underlying value. Okay, this guy here typically is not a function, this is typically a function that you can calculate from the data alone. This is a function that you cannot calculate generally from the data alone. It requires you to know the true value of theta. That's why I make a point of writing it as theta. Does that make sense? Okay. In fact, whenever you're designing an estimator, you can always compute the variance. It's, you know, you can look at this and say, this is just a simulation. I can always do this in a computer. I can generate data again and again and do this. But this you cannot, because you need to know what the underlying value of the parameter is. Okay, so putting these two together, what we had was the mean squared error. This is the variance plus the square of the bias. And the expression for this, the expected value, theta hat minus theta squared. Okay? I am only reviewing here the scalar case, but I expect you to know the vector case as well. Now, various ways of coming up with estimators. One of the things we looked at is it possible to minimize the mean squared error, this mean squared error? And oftentimes the estimators that you come up with for minimizing the mean squared error from this type of expression, these were not practical. Okay, oftentimes they're not realizable, precisely because they require knowledge of the underlying value of the parameter. So what we did is we compromised and we said, okay, what about we come up with estimators that we know somehow have a zero bias, and then we minimize the variance of theta hat over that class of estimators. And so this is what we called the minimum variance unbiased estimator. Okay. Now, unfortunately, these don't always exist either. Okay. Because I can easily come up with an estimator. I can easily come up with a problem where no unbiased estimator even exists. Okay, forget about the minimum variance part. It's not difficult to come up with problems Well, you can't even satisfy the first condition. Okay. Well, you might get lucky and you might be able to do this. Now, if you do, if you're able to come up with a minimum variance unbiased estimator, how small can this variance be? Okay. And this was given by the Cramerel lower bound. So this gives a lower bound on the variance of any unbiased estimator. So this is how it works. Variance of theta hat is lower bounded less than or equal to 1 over the expected value this is one way to write it. Another way to write it is 1 over the second derivative with a minus sign in front. And don't forget the minus sign. Okay, so these are equivalent ways of writing it. This theorem also, as a sort of second part, told us a way of possibly finding a minimum variance unbiased estimator. What it said was that if this score function, this is what we call the score function, if this could be written as I of theta times g of x minus theta, then theta hat equals g of x is efficient. And what that means is that it is the minimum variance unbiased estimator which achieves the Cramerel lower bound. Okay? And in fact, what I forgot to mention here is these quantities here, these, the ones in the denominator, these are called I of theta. That's the Fisher information. This is for the scalar case. Efficient is an interesting concept. It means that the estimator achieves the Cramerel lower bound for any value of theta, for any underlying value of theta. Okay? You may come up with a class of estimators, and amongst them, you may come up with a class of estimators that are zero bias, and amongst them come up with the one that has the smallest variance. You can call that minimum variance unbiased estimate. But that may not actually achieve the lower bound, in which case it is not an efficient estimator. Okay, so efficiency is a very, very strong condition. Okay? And so if you can write things this way, then you're sort of scot-free. Oftentimes what happens, and I think somebody asked me this last time, is you start with this left-hand side, and the problem is maybe complicated. And you kind of try to do this analysis and see if you can write it like this, and you fail. Okay? Don't jump to conclusions, because it may be that the problem is just too difficult for you to try to manipulate it into this fashion. You may still be able to find one, but it may just be difficult to write it this way. Okay? So, what about the vector case? In the vector case, this same theorem takes on a slightly different form. We write it as covariance of theta hat. So variance is just for a single parameter. Covariance has a vector in mind. We say this is lower bounded by the inverse of the Fisher information matrix. This does not mean element by element. I think I've mentioned this multiple times. It means that the difference between these two is a positive definite matrix, or positive semi-definite matrix. This is a big, important thing to remember. The Fisher information matrix, the ijth element of the Fisher information matrix, is minus the expected value of this second derivative, d theta I, d theta j. Okay? So mixed partial derivatives of p with respect to the ith and jth element of the vector theta gives you the ijth element of this matrix. Okay. Yeah.
This achievability of the Kramer lower band for the efficient estimator is done with a finite number of data, or
Finite number of data. Yeah, so the Kramer-Rao bound can be calculated for any number of data that you have. Okay? So basically what you're going to do is you're going to compute the joint probability density function for x, and x is going to have n elements in it. You're going to compute this derivative, you're going to square it, take the expected value, and that's your CRLB for that number of data points. Now what's going to happen is asymptotically, as you, well, let me draw a picture to answer your question. So you remember we drew a picture like this, so this is as a function of theta, and let's say this is the variance of theta hat for some estimator. So let's say the Kramer-Rao bound looks like this. I don't know what it looks like, but let's just draw something. Let's say it looks like that. And let's say for a particular estimator, we have this behavior. Okay, so we've calculated both of these for n data points. Now what happens is, let's suppose I increase the number of data points. What's going to happen is the Kramer-Rao data, Kramer-Rao lower bound is going to start coming down. Okay? This guy is also going to start coming down. They may or may not match each other at infinitely large number of data samples, but they might. If they do, then the problem is called asymptotically efficient. That estimator is called asymptotically efficient. Okay. And also, don't necessarily assume that the red curve, as the number of data goes to infinity, is going to hit 0. It may not. Okay. There are situations in which, if you have an unbiased estimator, you will never be able to hit variance of 0. It can happen. Okay. And so that's the asymptotic analysis of this stuff is actually quite an interesting subject, which many books have been written about it, and even more papers. But you see what happens is that the Kramer-Rao bound is kind of stuck between this and 0, right? So something has got to happen, and if you're lucky, what ends up happening is that the blue curve ends up catching up with the red curve, and you get asymptotic efficiency. Okay, so from the matrix case, we had the scalar sort of special cases of this, which was, what if you just, out of this whole matrix expression, out of this whole thing, what if you just wanted the variance for one of the components of the vector? So if you wanted just the variance of theta I hat, and I showed you two different bounds, one which you get by inverting this matrix and then looking at the ith component, and another one which you get by simply taking the ith component of the information matrix and just computing the inverse of that. And I told you that this is also a valid bound, but it is looser than this one. You can use it, but it's not going to be as reliable as this guy. It's not going to be as informative as this guy. And also remember that the general idea behind computing the Cramer-Routh bound is that it gives you an idea of how difficult it is to estimate a parameter. Okay? And this Fisher information gives you an indication of the level of sensitivity of the probability density function to the changes in the parameter. Okay? So somebody actually came to my office and we had a little discussion about the intuition of behind the Fisher information matrix, and I don't mind just kind of going over it quickly because I think it's probably useful for all of you as well. So if you've taken in most engineering programs, when you're talking about designing a circuit, you generally talk about something called a sensitivity function. Okay? So let's say you have a function, and let's forget about all the stuff that we just talked about. Let's say you just have a function, f of x, okay? And this function also depends on some theta, so let me just put a theta in there as well, okay? If you just have some function and it depends on theta and you want to see how much it changes as a function of theta, well, one way to do it is you just take the derivative of f with respect to theta, right? So we talked about, here's one example. Let's say I write f of x is alpha x to the beta. Okay, now I have two parameters, alpha and beta, and I'm kind of wondering, if I plot this function for some fixed alpha and beta, it might look like, it might look like that, right? Now what would happen if I change alpha? Well, if I change alpha, this will change, but probably not a whole lot, right? It might, it might look something like that, okay? Now on the other hand, if I change beta, I could really screw things up, right? I could make the curve look really different, okay? So it might, suddenly do this, or it might suddenly do that, okay? So obviously, there seems to be some level of sensitivity to changes in beta that is stronger than the changes to alpha, okay? So now I can measure that sensitivity by just taking derivatives of f with respect to alpha. And if I do that, then I just get x to the beta. And I can measure the sensitivity with respect to beta. And that gives me alpha, beta, x to the beta minus 1. Right? Okay. Now the way sensitivity function is defined in general is you actually normalize this derivative by the actual value of the function. Because what you're interested in is the relative sensitivity of the function to changes in the parameter. So the relative sensitivity is df d alpha divided by f. So in this case, this would be x to the beta divided by alpha x to the beta. And so you get 1 over alpha here. Okay? And on the other hand, df d beta divided by f. This is alpha beta x to the beta minus 1 divided by alpha x to the beta. So the alphas cancel out, and you get beta over x. Right? Okay, so two things to notice. First of all, here, this sensitivity actually does not depend on the data. Right? Does not depend on the x. Whereas this one does. And second, they depend on the parameter in a very different way. Okay, so what this quantity showed you is how much the function is going to change in relative terms as a function of small changes to the parameter. Now, if you look at this, this is the derivative of f divided by f. What's another way to write that? You can write it as the derivative of the log of f by alpha. This is exactly that. Okay? Or this is exactly that, right? Okay. Now in our case, x is a random variable, right? A bunch of data points. Okay? So if we're going to look at the relative sensitivity, which is this function, we have to look at the moments of this function, right? Its mean, its variance, and so on. It's a very simple way to look at how things change, right? So take the mean of this. If you take the expected value of this, what do you get? You get 0, right? This was the regularity criterion, so this actually gave us 0. So it turns out that the relative sensitivity, its expected value doesn't give us much information. So then what we do is we go to the next order moment, which is, you go to the expected value of this thing squared. Now that's the variance of the relative sensitivity. And what's that? This is the Fisher information. Okay? So this, I didn't really involve much statistical arguments here. I just showed you how you measure general sensitivity, and then how that sensitivity, when you measure its moments, you end up getting the Fisher information. So what's the Fisher information? It's simply measuring, in an average sense, the relative sensitivity of the function, which in our case turns out to be the PDF, with respect to changes in the parameter. Okay, is that useful? I hope. Okay. Okay, so in the remaining half an hour, what I want to do is, I posted a practice midterm exam from a couple of years ago, and hopefully you've had a chance to look at it a little bit. So what I want to do is go over it with you. This will give you a rough idea of what the midterm is going to look like this year. What I generally do is I give a few true-false questions, and then I give 3 or 4 actual problems to solve. So let's go over these and see if we can figure it out together. Okay, the Fisher information, first one. The Fisher information I inverse of theta lower bounds the mean squared error of any unbiased estimator of theta. Is that true or false? It's okay to think out loud. I'm not going to grade you on it. So if you want to shout something out, go ahead. It's okay if you're wrong.
It's true.
It's true because?
Because it's lower bands the variance, and therefore lower bands the mean.
That's close. It is true. The important thing to remember here is that because you're talking about unbiased estimator, there's no difference between the mean square error and the variance. Okay? So remember what the mean squared error is. It's the square of the it's the square of the bias plus the variance. Now here there's no bias. So the mean squared error and the variance are one and the same. Okay? Therefore, in this expression, I could have scratched off mean squared error and written variance, and then of course it would be true.
If you even didn't write that for unbiased estimator, it was true, yes?
No, because then the Fisher information is not, the inverse of the Fisher information is not exactly the Cramer-Rao lower bound anymore.
But it is a lower band, not the Cramer, right?
You can't be guaranteed that. That's not true. Because then the lower bound will have to involve the bias expressions, if you remember. It involved the bias and the derivatives of the bias. So if you just write 1 over the Fisher information matrix, depending on how the bias behaves, this may not be true. Okay? So yes, it's a tricky question. Okay. All right, so this is true. Okay, next one. It is always possible to find an estimator with 0 bias. mean, it's a quite an unreasonable thing to expect to be able to do. Okay, remember the definition of the bias. It's expected value of theta hat minus theta. There's no reason to think that it could be possible to find the zero bias estimator. Now the next one may be a little more interesting. It is possible to find an estimator. It is always possible to find an estimator with zero variance. What do you think of that? Pardon me?
False.
No. This is true. And the reason it's true is because I can always write a stupid estimator. Remember, theta hat is some function of the data, right? So I'm going to do this. I'm going to say theta hat equals 5. I don't care what data you give me. I'll always come out with theta hat equals 5. That's an estimator. And what's the variance of this estimator? 0. Okay? The bias is quite a nasty, ugly function here, but I've minimized the variance. Okay? So you have to be very careful with these things. What this shows you, the difference between these two, it kind of tells you where the hard part of the problem is. The hard part of the problem is controlling the bias oftentimes. Okay? Right, going to the next one. It is possible for the variance of an estimator to be lower than the one indicated by the Kremerau bound. And I'm clarifying that means the inverse Fisher information matrix for the problem. Okay.
There's no condition on bias.
Right, I haven't said anything about the bias, and that's the key to answering this question.
Yeah.
Right? So basically, the answer is true if you're willing to have bias. Right? So if I give you the Kremerau bound in the unbiased case, and you come up with a biased estimator, you can violate that bound. Okay? So this is true with bias. Okay, and then finally, the ROC curve for any detection statistic is always convex. The ROC curve for all the detection statistics you've seen is convex. But that's not always true. It turns out this is true, so this is false. It's true only if your test statistic is based on some kind of likelihood ratio test. Then you can be sure that the shape is always convex. Okay? Okay, so let's go to the next one. So this one says, okay, suppose we've collected data in a vector y according to a linear model, y equals h theta plus w. Theta is an unknown scalar, h is a vector, w is a zero mean random, not necessarily Gaussian vector with covariance c. A general linear estimator for theta is a function that behaves like this. Theta hat equals some vector a times the vector y. It's the inner product of some vector a with y. Now what you want to do is to find an expression for a so that the mean squared error of this estimator, find the mean squared error as a function of the a which we're trying to discover. Okay? So let's summarize what the problem is telling us. Okay, so what the problem is telling us is this part here. W is zero mean random variable with covariance C. What that means is expected value of W is 0 and covariance of W is C. We are not assuming that it's Gaussian though. Okay? The estimator has this form. We have to stick to it. So let's take a look at this first part. It says find an expression for the mean squared error. Okay, what's the mean squared error? The mean squared error is related to the variance and the square of the bias. So let's find each of those. Expected value of theta hat, expected value of A transpose Y, which is the expected value of A transpose, and I'm going to plug this in. H theta plus W. Okay? So this is expected value of A transpose H theta plus expected value of A transpose W. Right? Now the first part here, A transpose H theta, this is not random, so I'm just going to write it as it is. A transpose H theta plus A transpose W. Expected value of this is the expected value of A transpose, sorry, it's the A transpose times the expected value of W, which is 0. Okay? So this is 0. So this is A transpose H theta. So what you see is that the estimator is not unbiased. So the bias of the estimator is A transpose H theta minus theta, or A transpose H minus 1 times theta. Okay? So it's not unbiased. Then let's take a look at the variance. Variance of theta hat is the variance of A transpose Y. Again, plugging in the variance of A transpose H theta plus A transpose W. Okay? This part, A transpose H theta, is not random, so this is the variance of A transpose W. And this is A transpose covariance of W times A. Or A transpose C A. Okay? So the mean squared error is A transpose CA plus A transpose H minus 1 squared theta squared. So I'm taking the square of the bias and adding it to the variance, and that gives me the mean squared error. So this is part A. Okay? Okay, so part B is a little bit more challenging maybe. It says find A such that the linear estimator is unbiased and has minimum variance. So in other words, you're being asked to find the minimum variance unbiased estimator for this problem. And remember, the estimator is not arbitrary. The estimator has a particular form. It's linear. Okay? So what you're being asked to do is to find the linear, unbiased minimum variance estimator. Let's see if that's doable. Okay, so part B. What we're trying to do is to find the vector A such that A transpose H theta minus theta is equal to 0. Right? This is unbiased constraint, while A transpose CA is minimized. Okay? So this is the criterion we're trying to minimize, and this is the constraint we have to satisfy. And this has to be true for every theta, so the theta part really doesn't matter. This is equivalent to A transpose H equals 1. So that's the constraint. So you're minimizing a quadratic cost subject to a linear constraint. And this is simply done with Lagrange multiplier. So you write a cost function J of A, which is A transpose CA plus Lagrange multiplier times A transpose H minus 1. Okay? Now in order to do this, we have to take derivatives. Again, a reminder, how do you minimize something like this where you have a couple of unknowns? You have lambda and A. A is the thing you really want, and lambda is just a Lagrange multiplier you have to solve for. So there's a couple of steps involved in this. The first is you differentiate with respect to A, dj dA. You get 2CA plus lambda H equals 0, and you solve for A. You get A equals minus lambda over 2 C inverse H. Okay? But you're not done yet because you still don't know what lambda is. And in order to find out what lambda is, you invoke this constraint. Okay? So now we do the next step. So now you invoke the constraint A transpose H equals 1. So how do you invoke this constraint? Well, you just take this guy and you plug it in here. Okay? And so what you get is minus lambda over 2 C inverse H transpose H equals 1. And that says lambda is equal to minus 2 times H transpose C inverse H inverse. Okay, and now this lambda can be placed back in here to give you what A is. So A is H transpose C inverse H inverse C inverse H. Okay? So that's how you find A. This is your answer. So with this A, then the estimator theta hat equals A transpose Y is the unbiased minimum variance estimator for this problem. The beauty of this whole thing is that you got an answer to an estimation problem where you didn't even have to make the assumption that things were Gaussian. All you had to do was just assume that you know the mean and the covariance. You restricted your estimator not to be some arbitrary thing, but to be a simple linear function. And then you were able to optimize everything. Okay? I mean, in the past year, the past years, I should say, if I gave a problem like this, oftentimes the mistake that I notice is that people read the problem and then they assume everything is Gaussian. And they come up with an answer, and it may even be right. It may even have this form. But it's the wrong answer because this does not require you to assume anything is Gaussian. Okay? That's why it's powerful. All right. Okay, so the next one, hopefully we'll have time to do this. So the next one says you have a system that transmits either a signal S0, which has this form, or S1, which has a slightly different form. The only difference between these two is that there's a 1 minus alpha first here, and there's a 1 minus alpha in the second piece in the other one. And alpha is between 0 and 1. And the vectors Z1 and Z2 are chosen to be orthonormal. It means they're orthogonal to each other, they're perpendicular, and they have unit length. And what we're trying to do is to design this parameter alpha. And what we want to do is consider the following measurement model. So you're sending S0 or S1. It's going through the channel and being corrupted by some noise W, which is Gaussian with zero mean and covariance sigma squared times identity. And what you measure at the other end is X. What you're trying to do is to see which one of these signals was transmitted, S0 or S1. Now we're assuming that it's equally likely that a 0 or 1 is transmitted. Find the minimum probability of error decision rule. Simplify your expressions where appropriate. Okay, so let's remember these. These are the two signals, S1 and S0. Minimum probability of error decision rule in this case, where you have two Gaussians. So what you have here is a Gaussian with mean S0 and covariance C, and here mean S1 and covariance C. The minimum probability of error decision rule here was this T of X, was X transpose C inverse times S1 minus S0 plus 1/2 the norm of S1 squared minus the norm of S0 squared. Okay, and this gets compared to 0. Why does it get compared to 0? Because the minimum probability of error was the likelihood ratio compared to 1. Then what I did is I take logs of both sides of that. So this side became 0. I simplified. This is what I got. Okay? All right, now if you think about what S1 and S0 are, now you need to plug in here what S1 and S0 are and simplify and see what you get. S1 minus S0 is 1 minus 2 alpha Z1 plus 2 alpha minus 1 Z2. Okay? And S1 transpose S1 is S0 transpose S0, and that's equal to alpha squared plus 1 minus alpha squared. Now this, I hope, is not too confusing, because remember what S1 and S0 are. They're a linear combination of two orthogonal vectors, right? So if you have two orthonormal vectors, the magnitude of Z1 and Z2 are both 1, so the magnitude of the linear combination is simply the square root of the sum of the squares of these two. So that's why this is true. Okay? Okay, so if I plug these things in and I simplify, what I get is T of X is X transpose Z1 minus Z2 times 1 minus 2 alpha compared to 0. Okay, so this is my decision rule. So that's part A. Now looking at part B, for part B, we want to find the value of alpha that yields the smallest possible error probability. So what you have here is you have the minimum probability of error decision rule, but the minimum probability of error is still a function of this alpha, which you can tune. Right? So how should you tune it so that you get the smallest value of alpha, smallest value of the probability of error? This requires you to recall that for this type of problem, the probability of error is Q of 1/2 the norm of S1 minus S0 divided by sigma. Okay, for the minimum probability of error, this is basically, it depends on the distance between the two signals, normalized by the standard deviation of the noise. And this Q is the right-tailed probability for the Gaussian. If you now go back to what we had here, S1 minus S0 is this expression. If you compute the norm of this expression, it's again 1 minus 2 alpha squared plus 2 alpha minus 1 squared square root. That's what this numerator is. And if you simplify that, what you get is Q 1/2 times the square root of 2, absolute value 1 minus 2 alpha divided by sigma. Okay? And alpha, one has to remember, is between 0 and 1. Okay, so now the question is, how do we choose alpha so as to minimize this quantity? Okay. Now if you remember what the Q is the right-tailed probability. The right-tailed probability will be minimized when alpha is equal to either 0 or 1. Why? Because this expression inside will be as large as possible. The way you minimize the Q function is you maximize the argument of the Q function. So here, the min is achieved for alpha equals 0 or alpha equals 1. And in fact, that minimum probability of error is Q square root of 2 divided by 2 sigma. Okay, so you're done at this point. But if you want, you can also take these two, alpha equals 0 and alpha equals 1, and go up here and look at what that means for the signals S0 and S1. If you pick alpha be equal to 0, then this S0 is just Z2. If you pick it to be 1, then S0 is just Z1. So what this is telling you is you have designed a system which has a parameter that you didn't really need to design. Okay? In other words, if you have two signals Z1 and Z2, then just set S0 to be Z1 and S1 to be Z2. If they happen to be orthogonal and unit length, alpha is completely unnecessary. You don't need to mix them together. All you need is to transmit the two, and it'll work perfectly. I mean, not perfectly, but it will work to minimize the probability of error without having to play around with that parameter alpha. Okay? Okay, and then finally, problem 4. Okay, this is going to take me more than 5 minutes, but I think it's worth kind of taking a look at it because it's an interesting problem and it requires a fair amount of care to get it right. Okay, so you have two hypotheses, and you have you observe a scalar random variable x, which has an exponential density. So under H0, it behaves like e to the minus x. And under H1, it behaves also like an exponential random variable, except with a different parameter, 2e to the minus 2x. Okay, and x is always positive. And a priori, we know that the prior probabilities are 1/3 for p of H0 and 2/3 for p of H1, and these are the costs. Okay, so the costs are not equal. So there's more cost associated with making this type of error than it is to make that type of error. So now the question is asking you to find the test that minimizes the Bayes risk and to simplify your test as much as you can. So here's part A. So let's write down the f of x given H1, the f of x given H0. Probability of H0, probability of H1 times C10 minus C00 divided by C0 minus C11. You plug all of these things in, and this right-hand side turns out to be equal to 1/3. Okay? And what about the left-hand side? Well, the left-hand side, the numerator is 2 e to the minus 2x, and the denominator is e to the minus x. You're comparing these to 1/3, and therefore you have e to the minus x being compared to 1/6. Okay? Now I was very specific here, and I said be sure to simplify your test so that it is in terms of x, as much as possible. So when I say I want you to find the answer in as simple a term as possible, what I mean is I want you to give me a range of x for which I'm going to decide h1 and a range of x for which I'm going to decide h0. Okay, this is kind of implicit, so you need to be simplifying this even further. So now let me take this and let me take log of both sides of this. So if I take log, what I now get is minus x h1 h0 minus log of 6. Right? Okay. I want it simpler still. I want it in terms of x, not minus x. So I say x log of 6. Right? Now going from here to here, I have to be careful. I have to flip these. Okay, so I don't put h1 up here, I put h0. I put h1 here. Okay? Because I multiplied by a minus sign, the inequalities have to flip. And so now I can draw a range of x. See, this is 0. This is a log of 6. In this region, I'm going to choose h1. And in this region, I'm going to choose h0. And guess what? Here, I don't get data there because, oops, sorry, can't see it. Okay, here. Because x is an exponential random variable, I don't worry about this part. Okay. All right. So this last part of this problem says calculate the Bayes risk for the decision rule determined in part A. Okay. So in order to calculate the Bayes risk, what you need to do is to compute the error probabilities and then mix those error probabilities according to the weights that you were given earlier on. So the first thing we need to do is, well, I can write down the expression for the Bayes risk. Okay, so in this case, you're going to have C10, probability of H0, and then you also want to multiply this by the probability of choosing H1 when H0 is true, plus C01, probability of H1, times the probability of choosing H0 given H1 is true. Okay, so remember the Bayes risk had 4 terms in it, and 2 of the terms don't show up here because the coefficients in front of them are 0. Okay? So the 2 terms that show up are these guys. So in order to calculate this Bayes risk, what I need to do is to compute these probabilities, and of course I know these coefficients. So first, let's do this probability of picking H1 given H0 is true. Okay? So this is, okay, let me redraw the range. This is x, 0, log of 6. In here we picked H1. Here we picked H0. Right? So this probability is going to be the integral between 0 and log of 6 PDF of x given H0 dx. And this is the integral. e to the minus x dx, which if you carry out is 5/6. Okay, and then the other one, probability of picking h0 given h1. This is the integral from log of 6 to infinity. It's this range now. PDF of x given h1 dx. And this is the integral. 2 e to the minus 2x dx. And this turns out to be, after doing the calculations, is 1 over 36. Okay, so with all of this in place, and the risk is then 5/6 times 1/3 times 2. This is C10 plus 1 over 36 times 2/3 times 3. This is 11/18. Okay. Any questions? Okay, so that's where we're going to stop today. This should give you a flavor, anyway, for the kinds of problems that will be on the midterm. If you think these are easy, don't necessarily assume that the problems on the midterm will be as easy as these. If you think they're hard, don't assume they'll be as hard as these. Okay, these are just an example from whatever it was, 3 years ago. Okay, just to give you a rough idea of the kinds of problems I give. The main message is the types of problems I like to give are ones that will not require you to do 3 pages of ugly calculations. They will require you to have an understanding of what you're doing. Okay, so it could be the sort of thing where, you know, if you sit down and you end up doing 2 pages of, you know, really detailed calculations, and at the end it doesn't make sense, you've probably done something wrong. Okay, if you know what you're doing, you'll do well. If not, you'll probably end up doing a lot of calculations that get you nowhere. Okay? All right. So we will see you on Tuesday then. Oh, and don't forget to pick up your homeworks. They've been graded, and I will post the solutions to those as soon as I get back to my office.